We have discussed in our last class the vibrations of one-dimensional monoatomic molecules, that is the lattice with one atom in its lattice points. Today we will discuss about the diatomic molecule case, one-dimensional vibration. So for this, just as in the previous case, consider one-dimensional linear primitive lattice with basis consisting of two atoms, masses M and capital M. This is small m, which is capital M, where small m is less than capital M. So we are considering two atoms having different masses, one is less than the other, which are placed alternately along the x-axis with an interatomic distance equal to m. So this figure is shown here like this. That is, this is capital M. This is atom having mass capital M, and this is atom having mass small m, and they are alternately arranged in a one-dimensional axis. Here we are taking considering these atoms are arranged along x-axis, and this is a one-dimensional case, and these are connected by a elastic spring. Okay, this case is just similar to the one-dimensional monoatomic case. The difference here is that here are two atoms with different masses. One is less than or greater than other. In a state of equilibrium, let the atoms be located at sides represented by 2n minus 2, 2n minus 1, 2n, etc. And in the one-dimensional case, or in the monoatomic case, we have considered this positions as n, n plus 1, n plus 2, n minus 1, n minus 2, etc. Here, in the two-dimensional case, we are representing this by 2n, 2n plus 1, 2n plus 2, or 2n minus 1, 2n minus 2, etc. These are the positions where it is located, and it is the case of, and it is a state of equilibrium. And suppose one of the atom starts vibrating, and so it affects all the atoms since they are connected by a linear chain. So the displacement be represented like this. Suppose consider this atom. Consider this atom. So its initial position was this, and when it is vibrating, its position changes to this, and so this will represent its displacement, and it is represented by 2n, u2n, and similarly for this is u2n plus 1. The displacement for this atom is u2n plus 2, etc. So similarly on this side also. So these are the displacements of these atoms corresponding to each atom. And by considering the force equation, the initial part of this procedure is same as the one-dimensional procedure. So I needed to explain it again. And so I am directly going to the equations of motion. By considering the displacement of atom, the one atom is connected to the atom at the nth position is connected to atom at the n plus 1th position and atom at the n minus 1th position. So the effective displacement is represented by this expression. So the force expression will become like this, where beta is the force constant, and m into d square u2n by dt square is the force according to Newton's law of motion, where u2n is the effective displacement of the atoms in the position 2n. Similarly, if the force at the position 2n is represented by this equation, the force corresponding to the atom at the 2n plus 1th position can be represented by this. Here, note the point that small m at the 2nth position, the atom is atoms having mass small m, and 2n minus 1th position having atom having mass capital M, also for 2n plus 1th position, and for 2n plus 1/2 position the atoms having mass m. So they are alternately arranged. So the force acting on the atom at the position 2n is represented by F2n. Here the m is small m, and for 2n plus 1th position the force acting on is represented by this equation, and the mass is capital M. The traveling wave solutions of this type of equation are represented by U2n, which is equal to U2n is equal to a exponential I omega t minus 2kna. So correspondingly U2n plus 1 can be represented by b exponential of I omega t minus 2n plus 1 into ka. So we are representing two equations, two force equation, and the corresponding solutions for this two equation corresponding to mass small m and capital M for two atoms separately. This procedure you write down this equation just as we done in the previous case. So you will get this equation, this force equation. Okay. Here K is a wave vector of a particular mode of vibration. It may be noted that the vibrational frequency of both types of atoms is assumed to be same because both types of atoms participate in same wave motion. So here we are assuming that the vibrational frequency of both type of atoms are same because they are taking part in same wave motion. The amplitudes A and B may however be different because of different masses of the atoms. We are assuming that they have different same frequency because they are participating in same wave motion, but the amplitude may differ because of different masses of these atoms. So writing a similar expression for U2n minus 1 and U2n plus 1, 2, etc. and substituting this equation in the force equation, equation 17, we will get here in this equation we have U2n plus 1, U2n minus 1, U2n plus 2, etc. So we are writing down this this expression for displacement for correspondingly for U2n and 2n plus 1 to U2n plus 2 and substituting this in equation, and we will get the expression like this. Okay. So we will get equation 90, two equations, and we can proceed like in the previous case, and we will get we know e raised to ik plus e raised to minus ik is 2 cos km, and substituting this we will get 2 beta minus omega square m into a minus 2 beta cos k into b is equal to 0. These steps are explained in detail in the previous procedure, that is in the one-dimensional monatomic case. That's why I'm not going in detail in these steps. you can just write down these equations and can reach to this equation. Okay, you just do as a homework. So we'll get these two equations. So these are set of homogeneous linear equation, and this will have a solution if the determinant of this coefficient is converged to 0. So if we are writing down the coefficients as determinants, we will get an equation like this from this. So we are expanding the bracket here, and so these steps will come, And what we are doing is rearranging the terms, that is we are writing down the highest power of omega term first and then the next highest and so on, and so we'll get an equation like this, a quadratic, it's in the form of a quadratic equation, and from this we will get omega square, which is in the form of s square minus x square plus bx plus c. Okay, instead of x square, here it is omega raised to 4, so we will get omega square, just like we get x from the quadratic equation. So this is according to the solutions of that quadratic, that is minus b plus or minus square root of b square minus 4ac by 2a. From that we will get this expression from this equation, and the possible solutions of this equations are beta into 1 by m plus 1 by capital M plus or minus beta into square root of 1 by m plus 1 by m whole square minus 4 sine square ka by m into m. You may you may write down these steps in a separate notebook in detail if you want, otherwise it is easy. So this is the dispersion relation for this case, okay, for linear diatomic molecule. So from the in the previous case, I am just turning my pages back. Where is our previous relation? Yes. So this is our relation. This is our relation in the one-dimensional case. I have written down it here. So in the one-dimensional case, this equation was this omega square. The expression for omega was omega square is equal to 4 beta by m sine square ka by 2. In the two-dimensional case, it is the equation for omega, and which is related to k, and this is known as dispersion relation. So considering only the positive values of omega, we find that in the monoatomic case, there is only one value of omega for a single value of k, whereas in the diatomic case, there are two values of omega. Okay, so if we consider this equation, considering only the positive values, we will get only one value for omega corresponding to a single value of k. But here there are two values, that is one with a plus sign and one with a, means in the middle, one with the plus sign in the middle and one with the minus sign in the middle, and which is represented as omega plus and omega minus. So we will get two expression here. Okay. So if we are considering the expression for omega plus, we find that for k tends to 0, sin k is negligible, and therefore we get, so we are considering the equation omega plus, and for k tending to 0, what will happen? Sin k tending to 0 means this value is tending to ka. So we will get, wait a minute, this value is negligible, that is yeah. So when k tending to 0, this value is negligible, so we will remain with the terms 2 beta into 1 by beta plus 1 by m. Okay. And for k tending to pi by 2a, sin k is 1, and we will get omega plus square as beta into this expression. From this expression, we are substituting this value. What we will get is sin k is 1. So the remaining term here is 4 by small m into capital M, and here we are expanding this bracket according to a plus b whole square formula, and expanding this bracket and solving this equation. So we will get omega plus square as finally 2 beta by m. So we have find out two expressions for omega plus, that is for k is equal to when k tending to 0 and k tending to pi by a. Okay, pi by a or pi by 2a. Okay, pi by 2a. So these are the expression. This is for k tending to 0, the value of omega plus, and this is the expression for omega plus when k tending to pi by 2a. Okay, now consider the expression for omega minus and the similar cases of k tending to 0 and k tending to pi by 2a. When k tending to 0, we write down sin ka approximately ka. It is not neglected in order to obtain a non-zero value of omega minus. We have neglected the value. We have neglected the value of sin ka when k tending to 0. Here we are not neglecting it completely. Instead, we are taking it as a small value in order to get a non-zero value. So here one more term will be appear inside the bracket. So we'll get a term like this, and what we are doing here is we are taking the 1 by m plus 1 by capital M term outside, so it will appear in the denominator here, and we are writing that term as m capital M by m plus m whole square, and this term is common. And it is taking outside, so we'll get 1 in the first term and the remaining terms in the bracket. And so, and this is expanded as 1 minus 6 all to the power 1 by 2 form, and by keeping the first order terms only, binomial expansion, we will get this expression. That is because 1 and 1 will cancel out each other, and after solving this we will get the expression. Here again this is m plus m by m into m, so this m and m into m will cancel out each other. In the numerator there will be m plus m, and the denominator m plus m whole square, so 1 m plus m will cancel out each other, so we will get 2 beta by m plus m into k square s square. So we got omega minus as ka into square root of 2 beta by m plus m for omega minus in the case when k tending to 0. And similarly for k tending to pi by 2a, we get a solution similar to equation 24. 24 is this equation with the m, small m replaced by capital M. So we are applying this condition here when k tending to pi by 2a, sin ka will be 1. So we are arranging these terms. So instead of plus, here is a minus term. So after solving this, the final term will be like this, 2 beta by capital M. So these two expressions are similar. This equation omega plus and omega minus are same, except in the case of mass. Here it is small m, here it is capital M. Okay, so the plot for this dispersion relation along with these solutions mean omega plus and omega minus for k tending to 0 and k tending to pi by 2a are plotted here. This is the figure. So there is two branches, which is the difference from this monoatomic case. Here this branch is known as optical branch, that is omega plus, corresponding to omega plus, and this branch is known as acoustical branch, which corresponds to omega minus. In the x-axis we are plotting k, and this is omega. This is a dispersion relation graph, and we will explain, we will discuss the features of this graph here. So from this, the following features are observed. The allowed frequency range of propagation is split into two branches, an upper branch called optical branch and a lower branch called an acoustical branch. The acoustical branch resembles the dispersion relationship curve for a monatomic lattice, whereas the optical branch represents entirely different types of wave motion. It is quite clear from this graph. We have got two branches. So two branches for one is acoustical and optical. This acoustical branch is just similar to the one-dimensional monoatomic case, and this is a completely different branch. Okay, and the second observation is that there exists a band of frequencies between these two branches, for which the wave-like solutions means the solution, the expression for u are not possible. It means that it is not possible to excite vibrations in a lattice at a frequency which lies inside this band. This band is called forbidden band. That is represented by this region. So there is a forbidden region. This is actually forbidden region. So no vibrations are possible. No vibrations can be excited in this branch. So there appears such a band, forbidden band. The width of this band depends on the mass ratio capital M by small m. Okay, so the width of the, you have noticed, see, this is the optical branch, and the width of this is the width. So the width of this branch is depending on the mass ratio capital M by small m. So what does this mean? If the mass ratio M by M is larger, the greater the width of the forbidden band. If it is capital M by small m. If it is larger, the width of this band gap would be larger, and if it is smaller, the width will be smaller. So how can we explain that feature? Here note that this is the point where this is the point representing omega plus corresponding to k is equal to minus pi by 2a, and this is the point corresponding to k is equal to pi by 2a, which we have derived already, and this corresponding value of omega minus corresponding k is equal to pi by plus or minus pi by 2a, these 2 points, and this 4 corresponding to 0. Okay, here in the derivation we have assumed that Ka, then Ka tending to 0, sin Ka as Ka instead of 0 in the case of omega minus in the derivation, just to get the non-zero value. Here it is taken as a 0 value by considering K is equal to 0. Okay, so these are the that's how this graph comes. So here this is small m and this is small capital M. Note that this is small m and this is capital M. So capital M by M larger means M is larger or small m is small. That is the case. That small m is small means this value is greater, because small m appear in the denominator, so this value is larger. So this value larger means this point will shifting upwards when m becomes small. Similarly here, and m larger quantity means this quantity as a total becomes smaller because this quantity appear in the denominator. So this will shifting downwards, this 2 points shifting downwards. So that means this point is shifting upwards and this point shifting downwards, means the width of this forbidden gap is increasing. That's what we mean by this mass ratio relations with the forbidden region. So the forbidden region depends on the ratio of these two masses. Okay. The existence of the forbidden band is a characteristic feature of elastic waves in case of diatomic lattice. So this is a particular feature of this diatomic cases. If capital M is equal to small m, the optical and acoustic branch coincides at k is equal to plus or minus pi by 2a value, which is quite obvious. If small m and capital M are equal, these 2 points will coincide at the plus or minus pi by 2a value. The first brilliant zone is defined. The first brilliant zone is defined by k values which lie in the range k plus or minus pi by 2a. Therefore, the smallest possible wavelength of this zone is 4a, which corresponds to k is equal to pi by 2a at the zone boundary. So this represents the boundary, first brilliant zone boundary, and this and the smallest possible wavelength of this zone is 4a, which corresponds to k is equal to pi by 2a. Okay. Which is obtained from the since k is equal to 2 pi by lambda, which is pi by 2a, which will converge to lambda is equal to 4a. Okay. Now we look at the physical difference between the vibration represented by the optical and acoustical branches and determine the origin of the names of these branches. So we have named these branches as acoustical and optical branches. So we will look at how these names are came. So for optical branch, as k tends to 0, optical branch is the upper branch. For optical branch, as k tending to 0, cos ka tending to 1. And equation 20 yield, 20 is the equation that we have derived previously. So this is the equation 20. So when k tending to 0, k tending to 0 means cos k tending to 1. So these two terms, in these terms, cos k is 1. So we'll get expressions like this equation. So omega square is equal to omega, this is first equation and this is second equation. So we will get one equation like this and another equation like this. And if we divide these two equations are followed from these two equations, and we got two expressions, and if we divide these two expressions, we will get minus m capital B by small m into a. So this means a by b is equal to minus m by m. Here a is the amplitude of oscillations of mass small m, and b is the amplitude of oscillation corresponding to capital M. So this indicates that which is obvious from this expression, the solution, here, see this equation. U2n is the displacement or solutions of the wave equation corresponding to the wave which is produced by the atom in the 2nth position. Look at this 2nth position. Here the atom is small m. small m. So here its amplitude is represented by A. And look at the another equation U2n plus 1, which is the displacement of this atom or the solutions of the wave equation corresponding to this. So B represents the amplitude of this, the atom of the wave corresponding to this displacement. And then the 2n plus 1th position, this is capital M. So A represents the amplitude of vibration produced by small m, and capital B represents the amplitude of oscillation produced by capital M. So we have got this relation. So what does this indicates is that the two atoms moves in opposite direction. There is a minus sign here, so that's why we can say that the two atoms are moving in opposite direction and their amplitudes are inversely proportional to their masses. See, A is inversely proportional to 1 by m and B is similarly inversely proportional to 1 by m. So what does this means is that the center of mass of the unit cell remains unchanged because they are vibrating in opposite direction and their amplitudes are inversely proportional to their masses, so their center of mass of the lattice remains unchanged. Such a mode of vibration is shown here in figure. Okay, so this is the figure. There, these two different colors are represented for small m and capital M. Actually, I mean this as capital M and this is a small m. So they are vibrating in opposite direction, so that their center of mass remains unchanged. So this may be the equilibrium positions. It will not change when they are vibrating. When capital M becomes small m, A by B is equal to minus 1, which means even if their masses are equal, the atoms always move in opposite directions. Okay. Now consider the acoustical branch. Acoustical branch, for this, when k tending to 0, cos ka is 1 minus a k square a square by 2. This is according to the expansion of cosine series. We will retain with first two terms here. So we will get this expression. We have included the second order term on the RHS as it is the significant term in this present case. So this equation 20, just the equation, these are the equations 20. We will get from this expression, we are substituting for cos ka here, cos ka as this expression. So we will get these two expressions, and if we are adding these expressions, we get this expression. Adding this expression will leads to this. You may write down these steps in your notebook for details. Using equation 25. Okay, which is the equation 25. 25 is the equation of omega minus. This is the equation for k tending to 0. We can write down. So we have substitute that value here. It will become in this form, and by solving this in steps, it will lead to a by b is equal to plus 1. So we got a relation omega a by b is equal to plus 1. This means that the two atoms of different masses move in the same direction with the same amplitude as in figure B. So which means a by b is equal to plus 1. That means two atoms move in the same direction. This is represented as in this figure. Though they are of different masses, they are moving in same direction. And there is a movement of their centers of mass as well. So in this case, the center of mass may change when they are moving. We therefore conclude that In the optical case, the neighboring atoms move in opposite direction, whereas in the acoustical case, they move in the same direction. These characteristics features of optical and acoustical branches holds for their values of k, holds for other values of k as well. So we have discussed these cases for k is equal for k values plus or minus pi by 2 by or k is tending to 0. So these are valid for other values of k also. Here what is clear from this discussion is that in the optical branch the atoms are moving in opposite direction, whereas in the acoustical branch they are moving in the same direction. So what will be the conclusion? Can you guess? So the vibrations of the acoustical branch can be excited by a force which makes the atoms in a crystal move in the same direction. This type of effect may be produced, for example, by directing a beam of sound waves on the surface of crystal. You know how sound wave is propagating. The particles, so the vibration of motion is in the direction of propagation. It's there, so they are moving in the same direction. So this acoustical vibrations can be excited by a sound wave. So these vibrations are therefore known as acoustical vibrations. Monatomic crystals correspond to such vibrations. And in the case of optical branch, this can be excited by force which makes two neighboring atoms move in opposite directions. Optical radiations induce this type of vibrations in crystal, hence vibrations are called optical vibrations. Ionic crystals comprising two types of oppositely charged ions responds to such vibrations. So this type, the existence of atoms with different charges or different masses is not an essential criterion to induce optical vibrations in crystal. The mere presence of two atoms per primitive cell is the prerequisite for the generation of types of vibration. The diamond and HCP lattice, hexagonal close packed lattices having two atoms per primitive cell and exhibit optical branches. Okay, so the optical branch can be excited by light radiations or optical radiations inducing into the crystal system. So these types of crystal can be, these types of vibrations can be observed in ionic crystals where plus ion and minus ions are alternately appearing in the lattice points. But this is not a necessary condition for optical branches. The necessary prerequisite is that there should be two atoms per lattice points. That is the prerequisite for optical branches. And the example, diamond and hexagonal closed lattices can exhibit such optical branches. Now some interesting facts pertaining to diatomic lattices. So now we will discuss some interesting features or facts about this diatomic lattices. One is in diatomic lattices, the allowed frequencies constitute two frequency bands, one corresponding to the acoustical mode and the other to the optical mode of vibration. For polyatomic lattices having n atoms per primitive cell, the number of frequency band is capital N. So, since we are considering a two-dimensional diatomic cases, diatomic atoms, we will get two frequency branches. If you are considering polyatomic lattices having n atoms, we will get n bands of frequency. Okay, this is first fact. And the second one is, if all the atoms have the same masses m, the frequency range for both monatomic and diatomic lattice is the same. Omega square varies from 0 to 2 beta by 1 by m plus 1 by m. Here actually this expression was capital M, since if small m is equal to capital M, that is if the masses are same, m and m are same, so we will get 4 beta by m. 4 beta by m. In figure 8, this is nothing but this figure. Okay. So if the masses are same, all the atoms have same mass, the frequency range for both monatomic and diatomic lattices will be the same. Omega square varying from 0 to 4 beta by m. In monatomic lattices, the range is divided into two parts. In the first part, omega square varies from 0 to 2 beta by m, which corresponds to the acoustical branch. And in the second part, omega square lies in the range 2 beta by m and 4 beta by m, which corresponds to the optical branch. The forbidden gap is absent in this case, which we have already seen when we were discussed in the monatomic case, where the forbidden gap is different. So now the third point is, as the heavier mass m increases, capital M increases, the optical branch flattens and the acoustical branch yields downwards. That is as the capital M increases. Capital M increases means acoustical branch yields downwards. Acoustical branch yields downwards, and from this expression it is clear that this branch come downwards. Okay, so what's the final result? That is this branch flattens when capital M increases, that is this value is reduced. So because this term will become negligible when capital M is large, so this value is reduced means this become more and more flattened, and when this value become larger, this value become larger means this value is reduced and it becomes more and more flattened. And in the limiting case, when m tending to infinity, what happens is this branches exactly coincide with this k-axis, and which will be just as in the k-axis. So in the limiting case, when m tends to acoustical branch coincide with k-axis, and the optical branch becomes parallel to k-axis, and the upper curve become flattened to this k-axis and represents a single frequency square root of 2 beta by m. So which is represented here, this acoustical branch becomes k-axis and optical branch becomes parallel to this k-axis, and with a single frequency square root of 2 beta by small m, since in the case m tending to infinity. Okay, the physical meaning of this is that every atom in the lattice behaves as if it is completely free and isolated from its neighbors. So it is the case where the situation arises when the lattices are free and completely free to move from its nearest neighbor's influence. So it oscillates with its natural frequency square root of 2 beta by m. That's the case when m tending to infinity. Einstein used this model of lattice vibrations to develop the theory of specific heat of solids. We will discuss this in our next classes. It may be further noted that the allowed frequency bands gets compressed into levels. So instead of these bands, in this case the energy bands are reduced into energy levels. So we get energy bands when the atoms are bound in a solid, and the energy levels when the atoms are free. These are this feature we have already discussed in our band theory or free electron theory classes. Okay, you may be remembering this. Now the next point is, as the lighter mass small m decreases, the optical branch moves upwards while the acoustical branch is not affected. Now consider the case small m decreases. Small m decreases means this value increases. This value increases means this region, this point is shifting upwards. So that is, the optical branch moves upwards while acoustical branch is not affected, because there is no influence of small m factor in this branch, so it is not affected. When m tending to 0, the optical branch disappears altogether. So when m decreases, this optical branch moves more and more upwards, and when m tending to 0, the optical branch disappears altogether. This is expected as for m approaching 0, the lattice becomes monoatomic with a lattice constant k. This is a case of monoatomic case. That is, small m is completely vanishing, which means only a single atom is appearing. Okay. Now the next feature is the variation of amplitude ratio B by A with wave vector k for both optical and acoustical branches shown in figure here. So in the x-axis k value is taken, and the y-axis the ratio of amplitudes B by A. For k is equal to plus or minus 2 by A, the ratio B by A is 0. Here it is shown. This is k value. This is 0. Okay, and the amplitudes are for k is equal to plus or minus 2 by these two values, the ratio B by A is 0 for optical branch. So this is for optical branch, this is 0 for optical branch, and this is a high value or infinitely large value for acoustical branch. So this is not 0 here, but this is 0 here. Okay, this is shown here. This indicates that in the acoustical branch, all the lighter atoms with mass m are at rest. All the atoms with mass m are at rest. That means A is equal to 0. So we have taken B by A in the excess. So this value 0 means B is equal to 0. Sorry, we are talking about the acoustical branch. So this value infinitely large means A is 0. Then only this value will become infinitely large if we are considering the term B by A. And since we have plotted B by A on the y-axis, so B by A for the acoustical branch, this is the acoustical branch, all the lighter atoms with a small m are at rest. A is the amplitude corresponding to mass m, which means that all the masses m are at rest. And in the optical branch, what is the case? The amplitude is 0 at this pi by 2a value, which means B is equal to 0 here. Then only this value becomes 0 here. That is the mass with capital M are at rest. Thus, at the edge of the brilliance zone, only one of the sublattices is oscillating. Which means this is the boundary of brilliance, first brilliance zone. So what does this means? That at the brilliance zone boundaries, only one of the sublattices is oscillating. The sublattices of heavier atoms in the acoustical branch and one of the lighter atoms in the optical branch. The two modes have different frequencies if masses are unequal and represent standing waves with a phase difference of pi by 2. The two modes have different frequencies if masses are unequal and represent standing waves with a phase difference of pi by 2. For k less than pi by 2a, both sublattices vibrate, which is clear from this graph. Okay, so this is all about the vibrations of two-dimensional diatomic vibration, lattice vibration. Now, what is the significance of this theory? The theory indicates that the existence of frequency bands in the diatomic and polyatomic lattices. So, this theory indicates the existence of frequency bands, different bands in the diatom. In the case of diatomics, 2 bands. In the case of polyatomic lattices with n lattices, there can be n atoms, there can be n bands. And the bands are separated from one another by forbidden gaps. So there are appearance of forbidden gaps. And the crystals cannot propagate the vibrations of all possible frequencies. Only those frequencies are allowed which lie in the allowed bands. So these are the features or significance of this theory. Okay, these are all about the one-dimensional diatomic lattice vibrations. Okay.